grade 11 students. Hope all are okay. I'm your math teacher, Wissam Sharafi. Today's lesson is about complex numbers. We used to solve in R certain equations x squared minus 4 equals 0, factorize x plus or minus 2. And when we want to solve x squared plus 1 equals 0, we used to say no solution in R because x to power 2 is never minus 1. They tried to find a solution for such equations by creating an imaginary value, which is imaginary number I squared equals minus 1. This number does not belong to R. It is not a real number. So by creating I squared equals minus 1, they substituted, for example, x squared equals minus 1. It will become x squared equals I squared, and you solve it x equals plus or minus I, where I does not belong to R. Definition: there is algebraic form and different forms of a complex number. First, set of complex numbers is represented by this C, and Z is a complex number. It belongs to C if equivalent to Z equal A plus IB, where A and B are real numbers. It is important that A and B are real numbers, and I is imaginary such that I squared equals minus 1. So A is the real part of the complex number Z, B is the imaginary part of the complex number Z. If a complex number equals 0, for example Z, which is A plus BI or IB, is 0, then the real part and the imaginary part both should be 0. Two complex numbers are equal, for example Z and Z prime, if and only if the real parts are equals, A equals A prime, and the imaginary parts are also equal. For example, m plus 3 plus 2n minus 4i, this is a complex number, is equal to another complex number if and only if the real parts, m plus 3 equals 5, and the imaginary parts, 2n minus 4 equals 6. Okay, we said it. Z is a complex number, A plus IB. The real Z is A, we write it REZ, and the imaginary Z is B. Then, in this example, 3 is the real Z and minus 4 is the imaginary, because the equation or the number, the complex number is A plus IB. It should be plus minus 4I. If Z is a real, if Z is real, then imaginary part is 0. For example, Z, which is 3 plus n minus 1i, is real. There is no imaginary part, which means n equals 1. If Z is pure imaginary, then the real part is 0 and the imaginary part is not 0. For example, Z is m plus 1 plus 3i is pure imaginary, leads to the fact that A equals 0, m equals minus 1, and 3 different. The opposite of Z, which is A plus IB, is minus A minus IB. This complex number is opposite to this complex number. Application: this complex number and this one are opposite. Then we deduce that m plus 2 equals minus minus 3. You wrote it here. And m minus 1 equals minus 2. We wrote it here. Then you solve for the unknowns. Operations on complex numbers. We have Z, A plus IB, Z prime, A prime plus IB prime are complex numbers. Their sum, to find their sum, you add the reals, you add the imaginary parts. Their sum is a complex number whose real is A plus A prime and the imaginary is B plus B prime. Similarly, the difference is a complex number. The real is A minus A prime, the imaginary is B minus B prime. The product, here you distribute A prime plus AIB prime, IBA prime, I squared BB prime. Recall that I squared is minus 1. If you substitute for I squared minus 1, you will end up with AA prime minus BB prime. You take I common factor here into AB prime plus A prime B. This is the result of their product. Z equals A plus IB. Its conjugate, you represent it by Z bar, is A minus IB. To find the product, you distribute, you end up with, because minus IAB plus IAB will disappear, and minus I squared B squared, I squared is minus 1, minus 1 is plus. So the product of a complex number by its conjugate is A squared plus B squared. Z is a complex number such that A plus IB over A prime plus IB prime. You multiply by the conjugate, numerator and denominator. These numbers are conjugate to each other. You end up with applying the rule Z squared, A squared plus B squared, and you distribute the numerator. This will be the result. We ended up the product, or if you want to express such kind of complex numbers in its algebraic form, you multiply by the conjugate. This is the algebraic form of Z. It is A plus IB. This is considered to be B. Properties of conjugate. It is important that the conjugate of Z, and Z is A plus IB, is A minus IB. We said that before. The conjugate of Z is Z. Z plus its conjugate is 2A, because the conjugate, if Z is A plus IB, its conjugate is A minus IB. Z minus Z conjugate is 2IB. The conjugate of Z plus Z prime is the sum of the conjugates. The difference of the conjugates is the conjugate of the difference also. If you have Z minus Z prime, the conjugate of this will be conjugate of Z minus conjugate of Z prime. The conjugate of product is the product of conjugates. Also, the conjugate of the division is the division of conjugates. Application. Find Z plus Z prime, knowing that this is Z, this is Z prime. As we said, you add the reals, you add the imaginary. You end up with the sum of complex numbers is a complex number. The product, you apply on the rule, it is A prime, 3 times minus 1, we wrote it here, plus BB prime, minus 4 times 2, minus, plus I into AB prime, 3 times 2, plus minus 4 times minus 1, applying on the rule we stated before. Simplify a complex number or express this in algebraic form. You multiply by the conjugate, as we said, and the conjugate of 3 minus 2i is 3 plus 2i. You end up with 3 squared plus 2 squared, and you distribute, you end up with 4 over 13 plus 7 over 13i. This is algebraic form. Compare for application. You have Z prime. First you find their sum by adding the reals and imaginary. Then you find the conjugate. If the sum is 2 minus 2i, the conjugate of the sum is 2 plus 2i. Then you find the conjugate of each alone. Conjugate of Z is 3 plus 4i. Conjugate of Z prime is minus 1 minus 2i. And you add the conjugate, you end up with the same result as before. Hope you understood. Practice is important. It's your book, volume 2, page 165. Solve number 1, part 135, number 2, part 13, and number 3, 135. Till we meet again. Bye-bye.